Now recording chapter 13. This one is called Heat and Temperature, I think, or something like that. All right. So let's make it do. Today is 31st. We'll make this one do like Wednesday night or something like that. Is it 5% or 3% permissive time? Default points, attempts, we do 7. Score, after due date, yes. All right, homework category. All right. Let's use some, let's see what we got here. Thermodynamics, right there. Take a look at that. Conceptual physics, nothing there. Honors physics, nothing there. And let's go to physics library and see what they've got. Temperature and kinetic theory and gas laws. Humidity, evaporation, and boiling. What's that got to do with it? All right. Really? Its own chapter? All right, so we'll use those. And let's look at how many questions we have. Not very many. Expansion. We're only going to have like 3 problems. Well, okay. We really have no more questions. That drives me crazy.
At this point, I think they figured we've gone through all the difficult math stuff and we can just do that.
Yeah. I think I might assign you guys questions from the book at this point, just to do some questions. We might have to do some standard homework, some more traditional style homework questions, straight out of the book, on paper. I know you guys would be excited about that. I would program my own questions, but I just don't have time. Summertime is not a time to do that. Okay, so Let's actually go to 13.1, start off with temperature. You want to get out a piece of paper and write down your homework assignment here, because we're going to go do the problems and the exercises except that they show you the solution. Well, they show you the answer, they don't show you the solution. Well, sometimes they show you the solution. I'm not sure I really care about 13.1 so much. Let's look at 13.2. Okay, in 13.2, I would like to you to do the second problem here with the Eiffel Tower. Except I want you to choose another building randomly in the world. Okay? I want you to choose some other random building in the world besides the Eiffel Tower. And I want you to figure out how much it expands, assuming that the Eiffel Tower is made of steel. Now, assuming that the building is made of steel. The Eiffel Tower is actually not made of steel. Did you guys know that? What's it made of?
Copper or brass?
No, it's actually cast iron. Yeah. If I remember correctly. Am I right? I might be wrong. Now I got to find out.
Wouldn't the iron have oxidized?
Well, steel will oxidize just as much as Eiffel. That's not how you spell Eiffel. Eiffel Tower is wrought iron, so it's essentially cast iron. And it is painted to prevent it from rusting. But I mean, that is just impressive. A wrought iron tower. It was built over 200 years ago. Built by the same guy who built the Statue of Liberty.
Are we assuming that whatever building we choose is also made out of steel?
Yes, so choose any other building. I want it to be a nice, famous building. So pick a nice, famous building or edifice of some kind. Assume that it's made of steel. Pick one that's probably made of steel. 1887 to 1889. So not quite 200 years. 120 something years. So 30 maybe. So 130 today, right? Or this year, anyway. So pick another building. That's what you're going to do from this chapter. I like the railroad one since we're railroad people in this town, or in this area in general. How large an expansion gap should be left between steel railroad rails if they reach a maximum temperature of 35 degrees Celsius greater than when they were laid? The original length is 10 meters, but that's not the original length. They now lay rails of, let's go see how long railroad rails are now, and let's use that number instead. How long is a railroad rail? 11.89 meters. So that's what they did now. Sometimes 40 foot long, but they actually can be much longer than that now. Let's see what they are now. They're as long as, I think they're like a mile long now. That's 1880, so 2013, 108 meters, 120 meters.
So longer than football. Significantly longer.
Yeah, so they're pretty long. Now, but I actually think they can make them like a mile long now.
How would you even transport that?
They actually, it's really interesting how they make them and how they transport them. They make them by pouring the steel. They have to make the rails out of like 4 different kinds of steel at different parts of the rail. So the top of the rail is made of really hard steel. The middle of the rail is made of softer steel, and the bottom of the rail is made of really good tempered steel. So they're different. They're melded together. And they used to cast them where they pour the first layer of steel and then the second layer and the third layer. Now they pour them through a die mold at the top of a cliff in Japan.
They do what now?
They pour it through a die mold. It's kind of like a funnel that is shaped like the rail, and it gets smaller and smaller towards the bottom, so that when it comes out the bottom, it's just slightly bigger than the rail will be when it's finished. But when it comes out the bottom, it starts cooling in the air off this cliff, and it stretches to the size it's supposed to be as it falls off the cliff. And at the bottom of the cliff, they have a boat, a big ship that they just run these things out onto. And they're not maybe a mile long, but they're like half a kilometer or something crazy like this. And they just run these out onto this boat. And since they're so long, they bend like noodles. And so they just run them out onto the boat piece after piece and cut them off and run them out onto the boat and cut them off. And so they can make them super long these days. But let's go with the number they've got here. They've got 120 meters, 121 meters. Let's do that one. 121 meters. And that's kind of really a really good number. So that's this. We're talking about our homework. We're doing our homework directly from the book, this chapter.
13?
Yep.
Okay.
And probably 14, because we're not finding very many homework problems in these later chapters. So we're going to make our own. We're going to pull some.
So what do we?
So the first one is the Eiffel Tower problem, except you have to choose a famous building in the world instead of the Eiffel Tower.
But still assume it's made out of steel.
Still assume it's made out of steel. Go out and figure out how tall it is and see how much taller it grows when it gets hot. Then you're going to do the expansion gap problem with the railroad ties, and you're going to use 120 meters instead of 10 meters.
120 or 121?
Yeah, sure. 121, whatever you're going to use. Then let's do let's do let's do this one at the bottom where it says the density of water is 0 degrees. At 0 degrees is very nearly 1,000 kilograms per meter cubed. And the density of ice is 970 kilograms per meter cubed. I'm going to calculate the pressure necessary to keep the ice from expanding when it freezes. And so you're going to have a change in volume, and that's kind of a challenging question there, for sure. They've given you how to do it. I want you to let's see. Yeah, just go ahead and just work through that problem. Try not to look at the solution until you've got a good idea of how it's done and you're doing it. But if you need to look at the solution, do it. Don't copy the solution. Look at it, see what you're doing wrong, and then go back and try it yourself. I'm going to trust you. But that's a good problem to work through because it's fairly complex and has some interesting implications. So that is for 13.2. For 13.3, the ideal gas law, this is where we're really going to concentrate a lot of our homework, yes?
Real quick, what are the homework problems?
So you're doing the Eiffel Tower one with the building of your choice. You're doing the railroad one with 120-meter rails. And then you're doing the expanding ice pressure one, which is the last one in that section.
Okay.
And then the ideal gas law problems. Let's take a look here. And just do, you can, Cassidy, you can just do these problems and either fax them to me at the MPCC office or take pictures with your phone and email them to me or whatever. That works. But please do this in a very clean fashion. Draw a picture, write down your equations, you know, if there are any forces involved, make some vectors. Do this the right way. Solve your problem completely without numbers first and then plug in your numbers. Do it the way physics is done most cleanly.
Do you have anything from 13.1?
No.
Okay.
Then in this one, for the ideal gas law, let's do the first one, but instead of your pressure in your tires being 2.5 times 10 to the 5 newtons per meter squared, I want them to be 45 psi, 45 pounds per square inch. Instead of dropping your temperature from 35 degrees Celsius to 40 degrees Celsius, I want you to drop your temperature from 70 degrees Celsius down to negative 10 degrees. Sorry, 70 degrees Fahrenheit down to negative 10 degrees Fahrenheit. So you're going to have to do some conversions, change some things up.
So it's 7 degrees Fahrenheit to
70 degrees Fahrenheit to negative 10 degrees Celsius. Sorry, negative 10 degrees Fahrenheit. So 70 Fahrenheit to negative 10 Fahrenheit. Okay. Then let's do the helium-filled balloons with the scientific equipment. I like that one. We want to go, instead of sea level with a temperature of 10 degrees Celsius, let's do sea level with a temperature of 30 degrees Celsius. And go to an altitude where the temperature is negative 40 degrees Celsius. And the volume is still 20 times the original volume.
The volume is still 20
The volume
times,
will
you
still
said?
be 20 times, yeah, everything else will be the same except the temperatures. We'll go from 30 degrees Celsius to negative 40 degrees Celsius and everything else will stay the same. Okay,
So what's in the temperatures?
what's that?
What's the temperature
70 to negative 10 in Fahrenheit.
No, it'll be,
again? For balloons.
no, that's the first one. Yeah, the first one is 70 to negative 10 in Fahrenheit. The second one for the balloon will be 30 Celsius at sea level, but it'll be negative 40 degrees Celsius when it goes up to a higher altitude. For the balloon one. Let's see. Let's do the airplane passenger. The airplane passenger has this 100 centimeters cubed of air in his stomach. Before the plane takes off from a sea level airport, what volume of air at cruising level the cabin level pressure drops? Let's do it instead of 100 centimeters cubed though. Let's do 75 cubic centimeters of air. Then let's do the number density of gas atoms. The number density tells you how many atoms there are per cubic meter, right? So that's why it's just a meters to the negative cube, right? Because that's just a number of atoms per cubic meter. And they tell you the pressure is this, but I want you to do the pressure, a pressure of 2 times 10 to the negative 10, actually 2 times 10 to the negative 11 newtons per meter squared of pressure. And then calculate the temperature there. I want that temperature in Kelvin.
So the number, what did you say,
So the number of atoms will stay the same, the number density. The pressure will be 2 times 10 to the minus 11 instead of 2.75 times 10 to the minus 10. And
2 times 10 to the negative 11?
that's right. And then the temperature, they want you to calculate the temperature there. I want you to calculate that temperature actually in Kelvin, Celsius, and in Fahrenheit. I want to know what it is in all three temperature systems. This one's actually a really cool one too. In deep space. So there's the temperature of space right there, 2.7 Kelvin. It's like 1,000 times hotter than the temperatures we reached in the laboratory I worked in. So,
That's the temperature I like my bath water.
yeah. All right. That's good for now for those.
And that's how we made a Packer symbol. Not even that. I just
We have 7 questions so far, right?
I'm sorry?
We have 7 questions so far.
Do we have 7 questions so far, you guys? I haven't been counting.
Yeah, I'm sorry.
Yes, they have 7.
7, yes.
Okay, let's do the one where you're calculating the average molecular speeds at for atoms for helium at 5 Kelvin. I also want you to pick, actually, instead of doing helium, I want you to calculate so calculate the average atomic molecular speeds. Do this one here for 3 gases of your choice up here on the periodic table. The gas, you can choose really any atom you want on the periodic table and make it a gas. So for example, calcium you can choose because it can be made a gas and it can be cooled down. It's at 5 Kelvin, you'd be surprised how fast calcium is moving, even though it's a big atom. Helium really is cooking, really moving at those speeds. So here is another one. The escape velocity of an object from Earth is 11.2 kilometers per second. We want to express that in kilometers per hour. At what temperature would oxygen have to be to escape Earth's velocity? In other words, how hot does oxygen have to be to leave the Earth's atmosphere? So I want you to calculate that one. Their oxygen leaving the Earth thing. Then do the nuclear fusion one. Energy source of the sun, hydrogen bombs, fusion reactors. And let's go on to phase changes here.
Did we go into this section?
Not yet. We're going to do it today. Okay, so the problem here with the vapor pressure of solid carbon dioxide this is under the conceptual questions. It says, what is the vapor pressure of solid carbon dioxide? I want you to do that one and answer the can carbon dioxide be liquefied at room temperature? If so, if not, why not, so on and so forth, right?
So, which ones?
You're doing the problems that are associated with carbon dioxide in the conceptual questions. Now, if I can really swing it, which I think I can, tomorrow we'll do an experiment where we'll make liquid carbon dioxide from dry ice. I'll have to pick up some dry ice tomorrow. All right, and then the last one, humidity, evaporation, and boiling. We're not going to do any homework on that. So that's your homework for chapter 13. Let's go ahead and finish up chapter 13. We finished off, remember, with the ideal gas law. Now we're moving on to the kinetic theory, atomic molecular expansion, explanation of pressure and temperature. And
So there's 12 questions.
12 questions sounds right. Does that sound right, you guys?
Yep.
Yes, we're getting a yes. So we're going to introduce you to your first experience with a particle in a box. This is a very common and much used and much loved mind thought experiment that we do in not only in classical situations like pressure and temperature, but also in quantum mechanics and particle theory and cosmology, where we reduce a complex system down to a single particle inside of a single box, usually a cubical box. And usually we don't even consider the whole box. We usually just consider one side of the box, but we say that it's in a box. And in this case, we have a particle that is in this box, and it has some velocity going towards one of the walls of the box, and then it hits the side of the box in a perfectly elastic collision and bounces off the box going another direction, right? As it does that, there's a change in momentum of the particle, and the change in momentum of the particle is equal to the impulse or the force times the time that it exerts on the box. So if we figure out how much time it took for it to change its momentum, and we know its change in momentum, we can actually calculate the force on the box, on the side of the box. And also, if we know the area of the side of the box, we can take that force, divide by that area, and get a pressure. So using this very simple model that we call the particle in a box, we can actually calculate the pressure that a single molecule of gas or atom of gas exerts on a certain area in a box. And then we can mathematically expand that to the entire universe and say that we've got a theory. Welcome to a particle in the box theory, right? That's how we do it. We start at this very, very simple level, and then we mathematically expand it and extrapolate to the general idea. So what happens here in the end is that you get this. You get this really interesting thing goes on where you've got the change, you've got this average velocity going on, and you've got a mass, because there's your momentum, right? And you've got a number of particles. That includes however many particles are going to hit this box. And you end up with a 1/3 in the end to start off with. And that ends up equaling the pressure times the volume of the box. Now this should look kind of familiar. PV equals some constants, 1/3 and n, which are constants, and mass, which is a constant.
Looks like ideal gas law.
Yeah, it kind of looks like this ideal gas law we've dealt with before. So if we take out the n, which is a constant, and leave in the 1/3 mv squared, then that's equal to k times t, which is the ideal gas law constant, and the temperature, which means temperature is directly related to v squared. and mass. Mass v squared is kinetic energy, right? And so that's where this idea that kinetic energy and temperature are related comes from this particle in a box idea. Now we don't go through all this in great detail because it does require some calculus. You can kind of fudge it with algebra, but I don't think, well, they kind of do it here. So here's fudging it with algebra. Your force ends up equaling your change in momentum over change in time, just like I mentioned before. And then your change in momentum ends up equaling the momentum going in plus the momentum going out, because one of them's negative, so you get one of them minus the minus of another one, and so you end up adding them together. So you get 2 times the momentum of this particle. And since it's an elastic collision, its momentum in is equal to its momentum out in magnitude. Well, it's kinetic energy, it's velocity in. Anyway, it's a perfectly elastic collision, we assume. So anyway, it hits this wall. You get this change in momentum of 2m times v divided by delta t because it's force times delta t equals change in momentum. That's the impulse momentum term. Then you change your delta t into the distance this thing travels in the time divided by the time that it takes to travel. Since it's traveling across a box with a length of L, then the distance is 2 times L because it travels across, hits the wall, and travels back to where it started. And then divide that by its velocity, and that will give you the time that it took. So the velocity, again, is that v sub x. Then you get an equation that looks like this, where the force is equal to the m times the v squared, that's where that divided by vx gives you that v squared, divided by the L, and then we multiply by n for the number of molecules that we have doing this, because they're all doing this, right? And then now you have something for your force, but then we got to figure out what is our average velocity. Well, remember, velocities are vector things, and so we have to add them together like vectors, and so that means the Pythagorean theorem, right? The Pythagorean theorem says that the x squared plus the y velocity squared plus the z velocity squared is equal to the square of the total velocity average. And so we use this to get our 1/3. 1/3 on average of the velocity is going one direction, 1/3 on average is going the other direction, 1/3 on average going the third direction. And so they're all about 1/3, and that's where that 1/3 comes into the equation. So the velocity squared x is about equal to 1/3 of the average total velocity. And then you can plug that in there, you get that 1/3 in there. You have pressure, which is equal to force divided by area, so you take this force up here divided by an area, and then you get this equation where you have n times m times v squared over 3al, and al is equal to volume. Area times length, right? The area of one side of a box times the length of the box, 90 degrees to it, is the volume of the box. So that's where they get the PV equals 1/3 times n times mv squared. Simple as that. So there we've got, the only real fudging we had to do was to assume this part, that our average velocity was equal to 1/3 of the, one-third of the Vx velocity was equal to 1/3 of the total velocity. But that's not a huge stretch to make, so it's not a big deal. You can do it very exactly with calculus, but in the end, we have this very interesting thing where the pressure times volume equals this mv squared thing. We know that kinetic energy is equal to 1/2 mv squared. And so if that is the case, and you solve this part of the equation up here, you solve it so that multiplying, if you essentially put a 1/2 mv squared in here and then multiply on the outside by, put a 1/2 in here, multiply the outside by 2, you end up with 1/2 mv squared equals 3/2 k times t in the end. It's kind of a switch, it's kind of like a double substitution right there. And that's where we can actually make this equation that will solve for the velocity in terms of the temperature, or the temperature in terms of velocity. So the average velocity, they call this the root mean squared. They've got the average squared, so they take the root of that and they call it the root mean squared. And so your average velocity is equal to 3 times the gas constant K times the temperature, divided by the mass of the particle in a gas. So there's your average velocity And that'll get you through like half your homework right there, that one equation. Several of these other equations as you go through here will be helpful as well.
Are the main
And some
ones
of
that
those
we need to
problems.
get out of that entire conversion, the PV equals 1/3 MV, and.
That's a good one to keep, yeah,
and
for
the
sure.
kinetic energy one.
This one's a good one, the force one's a good one, the kinetic energy is a good one, and the velocity is a good one. This one's
Force
probably the best one.
equals the number one.
Yep. So let's do an example here where we calculate the kinetic energy and the speed of a gas molecule. The kinetic energy is equal to 1/2 mv squared, but it's also equal to 3/2 k times T. In this case, they give us the temperature, but that temperature in this equation needs to be in Kelvin. Convert to Kelvin, and we get a K of 293 Kelvin. Solution, plug it in, right? 6.07 times 10 to the minus 27 joules of kinetic energy. Doesn't seem like a whole lot. But remember, we're talking about a very small particle with a very small mass. And when you plug it into this equation to calculate the velocity, plug in the temperature and the mass, that small mass down here, right? It's going to give us, remember the mass is 4.65 times 10 to the minus 26 kilograms. It's going to give us 511 meters per second. 500 meters per second. What is this? Nitrogen. So this is air. Air moving around at 500 meters per second in a cold room.
Freezing cold room.
Well, it's not really that cold, but they're moving, right? They're moving. You should also notice that the kinetic energy doesn't care about the mass, does it?
Is the mass of the
Nope. It just doesn't matter. The kinetic energy, you can have two particles with the same kinetic energy and different speeds because the mass, right? The mass is different. For larger particles, a big kinetic energy can meet a slower velocity. For smaller molecules, they have to have a bigger velocity to get that kinetic energy, right? So it's completely independent of mass. It's not that it's negligible, it's just completely independent. Kinetic energy doesn't care, but the velocity does care what the mass is, for sure. However, you do have to remember that we're calculating the average velocity, the average kinetic energy. So while you have most of your particles moving at about 500 meters per second in nitrogen gas, up around this peak here, it drops off fairly quickly, but there are some particles that are going much, much faster, and there are some particles that are hardly moving at all, right? Most of them are within this range that we call the full width half max of this curve, which is usually from about here to here. So the average is actually slightly right of the peak, just so you know. And the funny thing is that the further things go out, the hotter they go, in other words, the faster they go, and the higher the temperature goes. Usually the lower this peak gets, the wider the distribution gets. So I think it's kind of interesting. So the average lengthens out and we get more and more that are going different speeds. So here is the escape velocity problem, right? The escape velocity, we know what it is. We know what it is, and we know that a gas has to reach that speed. We use that equation right here to calculate the speed of a molecule at a particular temperature, or to calculate the temperature of a molecule at a specific speed, which is what we want to do here. We rearrange the equation, we're going to square both sides. We're going to have T equals mv squared over 3k, and then we can calculate the temperature that it needs to be to get away. 1.98 times 10 to the 4 Kelvin. Nearly 2,000 Kelvin. Okay? Even though Kelvin is offset by almost 300 degrees Celsius, this is still 1700 Celsius. That's how hot. I mean, how many oxygen molecules in the atmosphere are that hot? Well, the ones coming out of volcanoes, maybe. But they're going to cool off long before they escape, you know. So they're almost never going to get that hot. Now, there is a small number of them that will get that hot and stay that hot and escape, but a very few.
enough so that we don't have to worry about.
Yeah, in this
atmosphere
curve right here,
flying.
this is essentially the curve for the velocity of air at sea level, right here. How many of these things are out at 1700? Well, at 1200, it's almost nothing. Go out 500 more, and it's nothing of nothing, right? It's such a small amount, you could actually count the number of oxygen molecules leaving. So,
And once you get high enough, doesn't, I know that there are a couple places in the atmosphere where, like, above this point, water doesn't exist because it's cold enough, it freezes and it falls. So it would be
yeah,
very
there's
likely
lots.
to get all the way through and out. Still
Yeah, something has to stay hot all the way up to the top of the atmosphere and then leave. Right? So it's very, very difficult for it to do that as it gets up there and gets colder and colder. Okay. Phase changes. So, what are the phases of matter? The three phases besides all the other ones? It's all liquid and gas, right? And we have this thing that we call a phase diagram, where it's also called a PV diagram, that tells you about the different temperatures. And actually, this is a VT diagram. So a VT diagram is volume on the y-axis, T, temperature on the x-axis, right? And what this is going to tell you is it's going to tell you how it expands as it gets colder. I mean, expands as it gets hotter and contracts as it gets colder, except for some things that do a little bit of both in both directions, like water. But PV diagrams are what we call phase diagrams as well, and they are pressure on the y-axis and volume on the x-axis. And the interesting thing about these is when you put them together, they start to create zones. You can start to create zones where you can see what the pressure and temperatures need to be in order for it to be at certain phases. So this first one here is so this, I don't know, they don't tell us what this is for, but anyway, you have these curves that go down through here, and you can see if you have a nice smooth curve, that means you never change phase. So in these ones up here, the pressure is really high and the temperature is increasing, and they never really change phase. But at this one, right here, it's got this bump in it. That's because when it gets that bump in it, it actually turns into a liquid-gas mixture. And then if you go on this one changes from a gas to a liquid here. So these blue things are called the liquid vapor region, which is where it's turning from a gas into a liquid or a liquid into a gas. So in this case, actually this one is liquid going in liquid to vapor. So this is liquid over here. This is where it changes from liquid to vapor, and this one is here is the gas out here. Same here, liquid, the melting or the freezing, and then the vapor region out here. And then up here, it's always a gas. Now, on all of these PV diagrams, there's a point at which you go from gas to solid or solid to gas, essentially without actually having to melt or anything else, or boil, or you can go from gas to liquid. But that's what they call the critical point here. Now, there's a critical temperature and a critical pressure, and that's the pressure, critical pressure is there, critical temperatures here. And all substances have their own critical temperature and pressure. For water, the critical temperature and pressure, the critical temperature is at 374.3 degrees Celsius, and the pressure is at 219 atmospheres. So it has to be at high pressure and high temperature for you to reach that critical point where it just vaporizes without having to really boil. But if you go down here to carbon dioxide, it's much colder, 31.1 degrees Celsius. That's just a little bit above room temperature. And the atmosphere is much lower, 73 atmospheres, compared to 219. So carbon dioxide is much easier to reach that point, that critical point. Now here is another diagram that does a very similar thing, but does it a little bit differently. It shows you all three phases in one, and this is the pressure temperature diagram, which is also called the phase diagram. Let's see, the PV diagram is not, do they call it the phase diagram? They don't, they just call it PV. But the pressure temperature diagram, they do call the phase diagram. This one's pressure, temperature on the x-axis. And what this line shows is the boundary between solid and liquid, which is this one and this one, the boundary between solid and vapor, and the boundary between liquid and vapor. And this one is for water. So this tells you if you're raising the temperature and you keep the pressure, if you keep the pressure constant and raise the temperature, which means you would be going on a horizontal line pressure, because the pressure doesn't change, but the temperature is increasing because you're going to the right. You would, if you started off here at 0 degrees Celsius, which is where water is frozen, and you're at below 1 atmosphere, and you start increasing its temperature, it stays solid for a little bit until it becomes liquid right here, right? If you're at 1 atmosphere, then it becomes, it's solid, 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 and right just below 0.01 degrees Celsius, it starts to melt, because this line is the boundary between solid and liquid. So that line is where it will melt in temperature, which is about 0 degrees. So you're going from a little bit below 0 to up to close to 0, a little bit above 0.
So the higher the pressure with water, the sooner it will melt?
Well, it's, yeah, the lower temperatures, right? So if you go higher in pressure, it melts at a lower temperature. And that is absolutely true. The more interesting one, I think, is actually when it goes from liquid to vapor. That's the boiling point. This line right here is the boiling point of water. And you can see here, as the pressure goes down, the boiling point goes down, right? So what does that mean for people who are trying to cook dinner on top of Mount Everest?
We're actually, the reason I was is because we were up on the mountains, and we experienced a little bit of that trying to cook
Yeah.
supper.
I mean, you can boil the water pretty easily, actually. But it's not hot. The temperature can drop to as low as like 50 degrees Celsius, which is lukewarm. And believe me, I've had more than my fair share of lukewarm, dehydrated food on top of mountains. You get above 12,000 feet or so, and you don't even have to go that high, 8,000 feet. 8,000 feet, and your water is just, I mean, you can touch it when it's boiling. It's just not that hot anymore. And so you're getting lukewarm suppers if you're doing dehydrated food, which is one reason why people who climb at high altitudes don't always eat dehydrated food. They'll usually bring up some cheese with them and some canned meats and other things like that. Even though they're heavy, it allows them to have a meal that's cooked all the way through instead of crunchy, because the water never got hot enough, right? Did you have a question, Cole?
So, is there a point where the temperature can be like extremely low, but yet it looks like it's boiling?
Absolutely, that's what they call the triple point. So at the triple point, when you're at 0.006 atmospheres of pressure, the temperature of the water is almost 0, and it's boiling. And it has ice floating in it, because it's on the intersection between the solid, the liquid, and the vapor. Now, to reach the triple point of water is difficult. You have to have very low pressure, so you have to put it in a vacuum container, or you have to put it under a slide of water, but I don't like that demonstration. It's kind of lame. You can hardly tell that it's at the triple point. But the triple point for carbon dioxide is much more interesting, because it's at a higher pressure. I don't know if they have it here. Let's look at a phase diagram for carbon dioxide real quick. And this is what I'm going to try to do for you tomorrow. I shouldn't have to try very hard. I just got to make sure I get my dry ice. So dry ice is carbon dioxide, and this is what the phase diagram looks like for carbon dioxide. I don't want to do that. That's kind of dumb. What did I just do? I just want to see the image. There we go. So here's our phase diagram for carbon dioxide. 5.1 atmospheres, right? temperature, negative 50 degrees, 6.7 degrees Celsius. That seems like it might be hard to reach, but it's not, because what am I going to start with? I'm going to start with solid carbon dioxide, which is even lower in temperature. So if I start with solid carbon dioxide, which is dry ice, I'm already below the temperature that I need to be at. I need to warm it up, actually, right? And warming something up is easy. I just put it on a hot plate and I'm done. But normally when you put carbon dioxide on a hot plate, what happens? Well, it's down here at the 1 atmosphere range, and we get it cold, hot, warmer, warmer, warmer. What does it become? A gas. We call that sublimation. It goes directly from a solid to a gas, and that's why we call it dry ice, because it doesn't get wet when it melts, because it doesn't melt. It just goes straight to gas. However, if I increase the pressure to 5.1 atmospheres and then heat it up, what can I hit? I can hit the triple point. I can even make it all liquid if I want, if I get enough pressure. But so what I do is I make a dry ice bomb. You ever heard of dry ice bombs? Take a 2-liter bottle, put some warm water in it, put a little bit of dry ice in it, seal it up, throw it in a garbage can, right? And it expands and expands and expands. And soda bottles are very strong. The polycarbonate is extremely strong. It has I think it can hold 10,000 psi or something like that. Polycarbonate is got incredible tensile strength. But eventually it's going to pop that lid off the top. And when it does, it makes a loud noise in it. And you can actually shoot the bottle a long distance. It's dangerous to be around when it happens. But if you put it in a garbage can or something to contain it, then the worst you're going to do is break the garbage can and scare a lot of people. I don't recommend doing this at home. Go to a neighbor's. Go to your neighbor's house and do it. Anyway. But it's kind of a fun thing. You can do a liquid nitrogen as well. But instead of putting it in a 2-liter bottle, I'm going to put it inside of a container that is made of 1/4-inch thick polycarbonate and has metal plates on top and bottom with seals to hold it all in, so we can get it up to 5 atmospheres without it breaking. And the idea is that you start to see not water, but carbon dioxide liquid forming on the dry ice. It was formerly dry, it's now wet ice. And then as the liquid starts to build up, you actually get liquid and the ice in the liquid. Now, say the dry ice was floating in the liquid, but it doesn't, because it's not water ice.
It'll sink.
It's dry ice. It sinks to the bottom. But you get this stuff, and if you get a little bit warmer, it starts to boil. And the really cool things that happens, I will save for tomorrow. I will show you what happens tomorrow, because it's something that you can make happen that's really cool. No pun intended. So that is the phase diagram for carbon dioxide.
So say if there was a lake made of CO2 and it froze all the ice goes to the bottom instead of
Yep. It would freeze from the bottom up instead of the top down.
So you would have a lake of solid CO2.
Yeah. And you'd be living on a very strange planet with a lot of pressure and low temperatures.
That should be very comfortable.
No. Besides breathing, poisonous CO2. But if you could, have a life form that could process CO2 and get its oxygen from that and its carbon dioxide, well, a bunch of plant people, that would be cool. Again, no pun intended. Okay.
So what we do is, if we ever find this planet, is we plant a bunch of trees there, leave, and come back in 1,000 years and see what happens.
Plant some trees and leave. No pun intended. I'm on a roll today.
I didn't even intend to do that on
Worst form of humor, right? Okay. Sorry.
I'm sorry, okay?
Oh,
I didn't
yeah.
realize that until you pointed it out.
So,
Nobody does except people who are obsessed with that kind of humor like me and Packer.
Mr. Bradley can make about a dozen puns about a trash can.
Yeah.
He did that on a band show.
Okay, so anyway, what makes a liquid stay a liquid? Well, when you've got liquids made of molecules that are going around all the time inside the liquid, and every once in a while they hit the top of the liquid instead of one of the walls of the container holding the liquid. What happens if they're going fast enough? They fly right out, right? That's how evaporation works. If it's a hotter liquid, does it evaporate more? Absolutely.
There's more movement of particles that's moving faster. So
What?
I can't fly out.
That's right. What's holding the particles in that aren't going fast enough to escape? What's preventing them from escaping? Gravity is partially doing it, but it's gravity is definitely playing a huge role in this, but it's not directly gravity. What's directly pressing on the liquid from above? Pressure, which is caused by gravity, of course. But it's the air pressure above, and we call that the vapor pressure of a liquid.
Are we still in 3.5 right now?
Oh, yeah, I think so. No, we're at the bottom of 3.5 here.
Okay, cool.
Yeah, 13.5. Vapor pressure part. So, the really interesting thing is if you lower the pressure above a liquid, you can actually make it boil. Or around a liquid, and you can make it boil. So, are you guys okay with watching a somewhat graphic death scene in a space movie?
Oh, absolutely.
Is this 2001: A Space Odyssey?
No.
That has the
So, let's see, is that that sounds right. Mars. I'm trying to remember which one this was. Mars. Let's see if we can find this one. There it is. That's the one.
Oh, I've seen
Mission to
Oh,
Mars.
Mission to Mars? I've seen this one.
Yeah, I've seen this
So they're in love, and he's going to kill himself to save her. So he just lowers the pressure. So what happens to him when he lowers the pressure around his head?
All the water in this bottle boils.
Yeah. So all of the fluid in his body would suddenly have nothing keeping it in, keeping it liquid. No pressure on the surface of it. So first, what's going to happen? His blood is going to boil, and all the liquids in his body are going to boil. And that's going to be painful and unpleasant. He's going to
Luckily, it was quick, I think.
So that's going to expand. All as it boils, it turns to gas and expands inside his body. And it burst all the blood vessels, burst everything in his body, all the cells burst, very quickly. Then all of that, the hottest, fastest moving molecules are going to escape in the form of gas. What's going to be left? Remember that curve has all those fast moving ones? What's going to be left?
Slow one.
The really slow ones. What's going to happen to the temperature of his body?
Drop.
And what's going to happen? He's going to freeze. So he boils and freezes to death at once. What a way to go! Boiling, which is the most painful, freezing, which is the least painful. Maybe it didn't feel like anything at all. Sorry, I don't mean to make.
average death effort.
That's right.
In the most extreme way.
But that is literally what happens. You literally boil and freeze simultaneously. They call it evaporative cooling. As all of the hottest, fastest moving molecules evaporate from a system that loses its pressure, what's left is the cold stuff that freezes at almost simultaneously. So it's and that's actually how they achieve the very low temperatures that are necessary for creating a Bose-Einstein condensate. In a Bose-Einstein condensate, they have a gas that has this curve, this big curve of hotter stuff, and then down at the left end, it has that really small number of really, really cold atoms, and the hot ones out here we don't care about. What they do is they create a bowl out of magnetic fields. And this bowl, they can lower the lip of the bowl. So it's essentially a bowl of magnetic energy. Anything that has a higher kinetic energy than the edge of this bowl leaks out the bowl. And then they slowly lower the edge of the bowl, letting more and more of the hot stuff out, until eventually the only thing they have left is the atoms that are at 0.0000001 Kelvin. And it's a very delicate and very difficult process, first of all, to trap the atoms in that bowl, because first you have to make the bowl and get the atoms in there, trap them in there. And when you do that, you have to trap enough so that when you let down those walls, you have enough to study when you're done. Because you're going to lose 99.99% of all the atoms you started with. So you have to trap a lot to start with. Because, I mean, you need at least a couple million left to do it. I mean, a couple million is not a lot, but it's enough. But you gotta be able to save a couple million. You gotta start with gazillions of these things, and be left with just a couple million, or maybe a few thousand if you've got really good instruments. But when you're done, you can have a few atoms left at 0.000001 Kelvin, which just happens to have a very low velocity. We're talking meters per second instead of hundreds of meters per second, maybe even centimeters per second at that temperature. So they're moving so slowly. When something's moving slowly, it's extremely easy to study, right? It's like studying birds. You'd rather studying trees rather than flying around all over the place, right? So, anyway.
Is what happened there similar in the movie The Martian, when he blows up the airlock and like they talk about how all the water boiled off?
Yep.
Would that be the same thing because
Yep.
the pressure lowered and
Yep.
everything dies?
Yep. And if we had time, we would watch The Martian because that is such a great movie.
I'm down
Yep.
for that.
I don't think we'll have time. Maybe we should make it one of our lab activities. I don't know.
Yes.
Yes.
Would you rather do that than do an experiment in Bernoulli?
And then we can
Bernoulli
just say
experiment.
that we're going to have to make some questions from the movie.
No, we just talk about what's good and what's bad physics. Can't stop that from doing that anyways.
No,
Let's see, you want bad
I'm
physics.
a movie heckler when it comes to bad science.
If you want some bad physics, have you ever seen the movie Independence Day?
Oh yeah.
You know the part where like they're shooting the alien and the alien was like flying across the room? I saw that right after we were talking about momentum right away, but that can't happen.
I don't know why, but I love video games with wacky physics.
There's a guy that there's a professor at University of Idaho who goes around to different places doing a talk about bad movie physics, and it's really funny. But his favorite ones are bad movie science in general. But his favorite ones are probably Superman one, the first Superman with the classic one, Christopher Reeves, when Lois Lane falls off the building in the helicopter and falls like 20 stories, and then Superman catches that helicopter and it stops it within 2 stories. So you calculate how fast that helicopter is going after it's dropped over 200 feet, and then he stops it within 20 feet, and the amount of acceleration would have broken every bone in her body and stopped her heart to boot and given her an aneurysm. She would have died from like 20 different causes from that catch. And then another one of my favorites is King Kong, right? King Kong, in order for his skeletal mass, his skeleton to support his mass, he would have to be 8 times wider than he was tall. And so if you remake the movie with King Kong 8 times wider than he is tall, it's a really funny movie. Like he steps into a building and takes out 4 buildings to the side, you know.
Oh, that should be the same with Godzilla too.
Oh, yeah, absolutely. So
Actually,
anyway,
Godzilla's taller, so it has to be equal.
there's a lot of really good ones out here though that talk about bad physics in movies.
Have you seen the movie The Avengers, the first one?
Probably, I can't remember which one it
we've
is.
seen all of them.
Have I? I don't know.
There's a part where Black Widow is like on one of the alien ships,
Oh.
and she's hanging on like barely, climbs up into it, and then jumps and stabs like the alien.
Oh,
back and the air resistance is low, and it's like
Loses
Well,
connections.
Never mind that we've got flying like alien bugs. Let's never mind the bad physics there. But
Even the logical bad physics.
yeah. Okay, so let's move on. I've been tempted to teach a class about bad science in movies, just for fun. Look call it fiction science,
I take it.
fiction science theater, instead of science fiction theater. It's like you guys ever watch that Mystery Science Theater 2000, 3000, whatever it's called? You never seen that?
Maybe. Yeah, if you showed it to me.
This is one of the best shows from the 80s ever. So it was essentially this, they'd watch a movie, some sci-fi movie, but it was, you were always watching it as if you were at the back of a movie theater. So you could see all the seats in front of you and, you could see shadows of things in front of you. But then there were always these three shadows in the front rows of seats, two robots and a guy. And they would be narrating the whole movie and making fun of it. And it was hilarious to watch. Let's see if we can find a good one here. They did so many of these. I want to see one where they're actually watching the movie. Anyway, those are just two robots, and there's the guy that did it. But when you actually were watching the movie was when it was so much fun. Let's see if they have it here. Here it is. So this is what it looked like. You were at the back of the theater and they were at the front. It was just such a funny show that where you could watch old, and they do everything from super ancient science fiction stuff to Star Wars and everything else, and just the funniest things. But anyway, definitely worth. I think they have it on Netflix right now. You should check Netflix. You should watch one of those right now. This is way better than doing physics, isn't it? Maybe it'll work, maybe it won't. Okay. You can see that I watch a lot of science fiction. Let's see here. Where's the search on here? Oh, here it is.
I'm surprised you're a science fiction guy. I figured you for a rom-com guy.
No, I am definitely a science fiction guy. Mystery Science Theater 3000. Yes, right here.
I go into hyperspace and get nervous. We now take you live inside of L, the robot's hand. I'm good at space.
Anyway. Oh, you gotta love it. Okay, back to physics. Let's see, where are we?
This is physics, sort of.
Well, check that out. That's
We're
just awesome.
learning about what is not physics.
Oh, gotta love it. All right, let's get serious again. Okay, so partial pressure, vapor pressure, all that stuff keeps things from boiling. Moving on. Humidity, evaporation, and boiling. Here they talk about, here they give you the vapor pressures, saturation, vapor densities, temperatures. So we're talking essentially about what's happened. This is for water, I think. Yeah. So if water at negative 50 degrees has a vapor pressure of 4 Pascal and a saturation vapor density of 0.039, which tells you essentially when it's going to rain outside. So this is kind of weather channel stuff, which isn't all that interesting to me, but living in Nebraska makes it more interesting. But you can essentially, this is how they figure out if it's going to rain. If they can calculate the temperature outside, and then they calculate the pressure, or they don't calculate, they measure the temperature, measure the pressure outside, and then they know from a chart what these numbers are, and they can say, well, there's a 90% chance of rain, because as soon as you reach that vapor pressure and temperature, then water is going to form in the clouds. So you're going to get liquid water forming in the clouds. It's going to start falling. So that's what that's all about.
It's always interesting when they say it's a 50% chance of rain.
Yeah.
Okay, so what are you telling me here? You don't know?
Well, what
Tell
they're
me if I flip a
really
coin
what they're
with
telling
both
you,
ends.
and there is science behind it, because what's going on is that they have usually what's happening is a low pressure region is coming in, so the pressure is going down and getting close to that vapor pressure that where it will turn to liquid. And as that pressure goes down, if the temperature also goes down, then it will rain. And so they're saying they're looking at the charts and they're looking at the maps and they're looking at the different zones of temperature and pressure that are being taken from these they've got these weather stations out at the airports and at city centers. They've got them everywhere, and they take all that data and they say, well, from what's going on right now, there is about a 50% chance that this system is going to come down here and cause this pressure to lower. And so it's all from math and statistics.
No, they're just not sure that roll a dice and ask you what you
Well, the problem is that there are about 17 equations that determine how weather's going to work, but there are like 27 unknowns. So 10 things they have to guess on every day. And they use computer models to guess on those things, but still, it's just a guess. So about 1/3 of what they do to figure out the weather is guessing. And that's about right. About 1/3 of the time, they're wrong completely, right? And unfortunately, this past week, they were wrong. They said it wasn't going to rain, and it did.
Yeah.
And I didn't want it to, because I was building my house. But anyway. Okay, so chapter 14 is next. What time is it? 5 o'clock. Let's go ahead and get started with chapter 14 a little bit, and we'll do the homework for 14 tomorrow. We'll set it up tomorrow. But in this one, we're going to talk about how heat moves. Now, what is heat? How is heat different from temperature? We talked about this a little bit.
transfer that.
Yeah, heat is the transfer of thermal energy. You can look it up. I mean, it's right here.
Yeah, that's how I
But
got
what is temperature?
a measure of kinetic energy.
Yeah, it's just straight up energy.
Yeah, it's the measure of the kinetic energy, which is related to the thermal energy. So temperature is the measure of thermal energy. It's how much energy it is. Heat is when that thermal energy goes from one object to another by some transferal method. So here's an example. We have this can of soda and this block of ice, and they have two different temperatures, and they're on this block of something, foam, that doesn't allow them to come in contact thermally with each other. In other words, heat does not transfer through styrofoam very, very easily. That's why you make things like coolers out of styrofoam, right? Because heat doesn't transfer through them. Hot won't go through them very well, and cold won't go through them very well. Hot's the only thing that really goes, but that's okay. We'll learn about that later. So, in order to cool off your soda, you put your ice next to it, right? And then it's in contact with it. Then the heat can go from one to the other. Which one does it go to? And which one does it go from? Heat goes from the warmer soda to the colder ice. We assume that the soda is warmer than the ice. But the heat goes spontaneously in nature from hot objects to colder objects. Okay? Doesn't matter what the objects are. In nature, it naturally flows spontaneously from hot to cold.
So that'd be like why the sun's heat travels outside. of
That's
the sun
correct.
it's traveling.
That's why we get warm from the sun, right? Instead of the sun getting cold from us,
Very important.
right? You can make heat travel in the opposite direction. You can make heat travel from something that's colder to something that's hotter, but it won't do it spontaneously. You have to force it to do it. Can you think of an example of when we might do that?
Refrigeration.
Refrigeration. What else? Can you hear it running right now? Air conditioning, right? That's exactly right. In fact, in this building, it's kind of interesting because this doesn't use true air conditioning. This is a geothermal cooled and heated building. They're actually pumping up cold water from wells out in the field out here, and that cold water is cooling the air in this building, and then we run the air through the building, and then we put that water back down. But it's still the same idea. We're going from a colder to a warmer, right? We're making this area colder.
I always thought it was just introducing, like, if you have something hot, you just introduce enough cold stuff that the heat fuses.
That's not the way refrigeration generally works. We use geothermal here, so that's the way it works here. But refrigeration and air conditioning don't work that way. Refrigeration and air conditioning actually take the cold, they actually take the heat in the colder place, which is inside the refrigerator or inside the air conditioned house. It takes the heat that's in there and actually takes it to the outside and puts it in the hotter place. So in this building, we use cold water to cool the air.
We introduce something
But-
to go to.
we just have warm air come next to cold water. The warm air heats up the cold water and carries that heat away. So this isn't true air conditioning. But in a truly air conditioned house, you're literally taking heat from a cold place to a hotter place. And that's why you have to use so much electricity, because you actually have to, well, we'll learn about it later. But anyway, it's kind of interesting. So this is the machine that gave our friend Joule his fame. He was able to connect kinetic movement and energy, essentially. He was the guy that figured out that heat and kinetic energy are connected, and potential energy, gravitational potential energy. How did this work? Well, he wound up the handle here and lifted up these masses that were connected to this drum and these pulleys, lifted them off the ground, some certain height. And then he let go of the handle and he measured the temperature change as these masses fell down through this height and turned those paddles inside the tank. And he measured a temperature difference inside the tank. And he was able to say that mechanical movement and mechanical energy have the same kind of thing as thermal energy. You can transfer thermal to mechanical and mechanical to thermal. So what you're looking at here is really kind of the first way to go from one kind of energy to another, right here. That's why we name energy units joules. Okay, so let's talk about different objects. We already did the experiment with this guy right here, where we noticed that the different kinds of metal transferred the heat differently, right? So some of them got hotter faster, some of them got hotter slower. How does that work? Well, how are we going to describe that? We're going to describe that by doing some measurements of how fast things heat up and giving each kind of material its own constant, which we're going to call, what do we call that? Temperature, something. Specific heat, that's what we call it. We call it the specific heat of the object. So every material is going to have a specific heat C, and it's going to, let's see, what do I want to say? It's going to depend also on the mass. So if we have more material, we're going to be able to transfer more heat. Does that make sense? It's kind of like a highway. If you have more of it, it can handle more heat exchange, or more energy, thermal energy can travel through it. So the mass matters. What it's made of, which is this specific heat, each material will have its own specific heat, so what it's made of matters. And then the change in temperature is going to matter, because if you have a bigger change in temperature, you're going to have more heat traveling through it. This is what we call the specific heat equation, and Q is the amount of heat. So the big capital Q is amount of heat. So here we have a 0.5 kilogram aluminum pan on the stove, and we're going to use it to heat 1/4 liter of water from 20 degrees to 80 degrees Celsius. So there's our change in temperature. What are we going to use for our specific heat? What material do we have? Aluminum, but we also have one more. We also have water. So we're changing the temperature of two objects, the aluminum pan and the water, right? We want to know how much heat is required to do this, and what percentage is used to raise the pan, the water, the pan, and the pan and the water in the pan. So we're essentially going to be doing this twice. Once for water, once for aluminum. Here is the temperature change. It's going to be the same for both. Here is the equation for the heat that is required to heat up the water. We're using the temperature change of 60 degrees, mass of water times the specific heat of water. That's just looked up in the table below. Do the same thing for the aluminum, mass of the aluminum, specific heat of the aluminum, temperature change is the same. You get 62.8 kilojoules and 27.0 kilojoules. Is it true that it takes more energy to heat water in a pan than it does to heat the pan itself? How quickly does a pan heat up if you leave it empty? Very quickly, like dangerously quickly, right? Like could take seconds if it's an aluminum pan or a copper pan. How fast does it take if you fill it full of water?
Wow.
It could take as much as several tens of minutes, right? Depending on the size of the pan, how much water you put in it. So we add up the total heat that is transferred into this to heat up the pan and the water. We get 89.8 kilojoules. Then to get the percentage, we divide the smaller one by the bigger one. We get 30% for the pan and then 69.9% for the water. Sorry, we divide the littler one by the total and then the bigger one by the total to get those two percentages. Pretty straightforward. So, what happens if you're going down a long, steep hill and you keep your brakes on all the time? Has anybody ever had this catastrophe happen to them?
We saw it when we were up in the mountain, go around with truck drivers.
I actually had this happen to me when I was on my honeymoon.
Oh.
We didn't realize that the brake drums or the brake discs were as thin as they were on the car that we were driving. We had just purchased it used, and they were extremely thin. And they got hot and hotter and hotter and hotter to the point that they actually started to melt. So we started to lose our brakes entirely. So we pulled over, let them cool off, and then we drove very slowly using gears and pulled over quite often to let them cool off a little bit. And then we replaced the brakes in San Francisco. That's an expensive place to replace your brakes. But anyway, the point is that is another example of the mechanical energy becoming kinetic energy. You start at the top of the hill with what kind of energy?
Potential, gravitation.
That's right, gravitational potential. As you start going down, getting faster, what does it turn into? Kinetic. And then as the friction of the brakes comes into play, you're turning it into what kind of energy? Heat energy. You get materials heating up from friction, and that heat energy has to go into those materials. It also goes into the air. Have any of you seen disc brakes up close and personal? Yeah? What do the discs look like? They're perforated with holes, right? Why would you put holes in them? To lower the friction and increase the airflow. Cool them off. It doesn't make them better brakes necessarily. It actually makes them worse brakes. But it cools them off, which makes them better brakes, right? So there's kind of an optimal amount of brake to hole ratio that allows them to cool and not start melting. Okay. So here they have you calculate the change in gravitational potential energy and then the temperature from that amount of energy. In this case, they're equating the heat energy to the gravitational potential energy. They're assuming that all of the potential energy is arrested by the heat potential energy, or by the heat energy, which is pretty much true.
So that would be if you're going down a hill and you slam on your brakes and come to a complete stop.
Well, it's going down a hill even if you hold them down the whole way. You're slowing your car down, and that potential energy, which became kinetic energy, is becoming heat energy. And it all becomes heat energy if you stop. If you come to a stop at the bottom. Now here's an interesting one here. In electric cars and in locomotives, they actually use brakes that turn that heat energy back into electrical energy. Because heat can be turned into electrical energy. You can do it by turning a turbine, but you can also use a device which is called a thermoelectric device, which creates electricity when it's hot on one side and cool on the other. So they put the side that needs to get hot next to the brake, and they put the side that needs to be cool on the other side with a big heat sink on it to cool it off even better. And then they can create electricity, but they can also create electricity by reversing the polarity of their motor, their electric motor that they normally make it go with, and then it turns into a generator. So you can turn your electric car into a generator as you go downhill. And trains do this. Locomotives and commuter trains do this when they're going downhill. They actually reverse the polarity on their motors on their wheels, and they use that to slow them down. And then they're creating electricity and charging their batteries the whole way they're going downhill. They don't even have to turn up, and they get to the bottom and they've got full batteries and they're good to go. Don't have to turn on their diesel engines for a while. So there's actually even a way to transfer that energy through the tracks to another train going up the hill on the other side. So that's kind of cool. But anyway, you calculate that change in temperature from all the other stuff that they had. So here are the specific heats. Specific heat of aluminum, 900. So it's 900 joules per kilogram degrees Celsius. So this tells you how much energy it can hold per mass for every degree Celsius that it's going to change temperature. So aluminum can hold 900. How much can water hold? 4,000. That's why it takes so much more energy to boil water. And that's why we cook in water. Because if you boil water, how much energy is in it? A lot. 4,186 joules per kilogram of water per degree Celsius. So if you get it up to 100 degrees Celsius, you're talking lots and lots of joules. So you have a lot of energy in boiling water, so you can use it to cook anything, right? How about oil? Is oil on here? Right here. Glycerin, which is pretty close to oil. Half as much. Does that surprise you? Frying things takes it's so quick. Well, you can actually get oils up to higher temperatures before they boil. So that's the good thing for oils. They can be at higher, some of them can be at higher temperatures so that you can get them at a higher temperature so you can cook things faster. You can actually get more energy in them. But water, extremely high, you can get a lot of energy into water. And water, when it's boiling, is dangerous. Very dangerous.
There was, I think there was a news story about a guy who, his daughter came over from the mom's house because they were divorced, like in this area, and like she dyed her hair with like fluid dye or something. And he found online that you're supposed to use boiling water to get it out, and now he's going to be in jail because he gave her third-degree burns of boiling water.
Yeah. So essentially, the lower you go, the faster you heat up, right? So if you're using pans made of copper, you're almost 1/3 the speed to heat up your pans as aluminum, right?
That's why copper is used for a lot
That's
of wires.
that's why. Well,
And if you use a gold pan,
yeah. If you use a gold pan, you'll be cooking really quick, right?
I'm making all my pans.
Or a lead pan. If you use a lead pan, you might be melting your pan because there's a low boiling temperature.
Besides the fact that you're probably giving yourself
Little heavy metal poisoning never hurt anybody.
Mercury pan. All my problems solved. Let me know how that works out.
Look here, though. It's about evil. It's about the same aluminum and concrete, so you can bake in a concrete pan. You know? No big deal.
We can make concrete.
That's a lot heavier.
They don't have iron. Oh yeah, they do have iron here. Iron's 452, so cast iron is actually even lower than this. But iron makes a really good pan, and a lot of people like to cook in cast iron for that. It is heavier, but copper itself is quite heavy as well.
And cast iron, it sucks to clean.
Cast iron is difficult to clean, difficult to care for. Copper is also, because in order for copper to have this low specific heat, it has to be polished.
I'm thinking
But-
like with cast iron, it's porous, so you can't use soap and water.
Yeah,
You have to use
cast
soap
iron you
and
have to just scrub out and use hot water, and that's it.
There's
So a lot of people like to use aluminum pans because they're not bad, but they're not not great either. But anyway, so yes, sir.
I just realized on the list, water is the only one that has a higher number than the human body.
Yes, because the water is the human body's mostly water, but not quite all water, right? So your body can handle a lot of heat. So let's talk about what happens with phase changes in heat. My favorite way to describe this is to use this graph right here. This is the, I don't know what they call this really. But anyway, this shows the phase changes as a function of temperature versus heat. So this is the amount of heat you're putting in, 100, 200, 300, 400, in calories per gram or joules per, kilogram or whatever. So this is the amount of energy you're putting in. This is the temperature that it's changing as you put the energy in. If you go backwards, you're taking the energy out. So we start here at 0 energy and negative 20 degrees Celsius. So we're not putting any energy in right now, but we start putting energy in at negative 20 degrees Celsius, and look what happens. What happens to the temperature as we start putting energy in? Starts going up. Did you know that ice can be different temperatures? Yeah. If you take a really cold piece of ice out of your freezer, it sticks to your tongue. Why does it do that?
Because it's freezing the water.
Because it's freezing the water on your tongue and sticking to that frozen water on your tongue, right? So it's actually cold enough to freeze liquid water. So it's colder than 0 degrees. So it can pull some of that heat out of that liquid water on your tongue. But eventually what happens when we get to 0 degrees Celsius? We keep adding heat and the ice is warming up and it warms up to 0 degrees Celsius. What happens here to the temperature as we keep adding energy here? Stays the same. Stays at what? 0. What's happening while we're adding energy, but it's staying at 0 degrees? It's changing from ice to water, right? And we have to add almost 100 calories per gram of water in order for this to go from completely solid to liquid, completely liquid. And the whole time we're doing that, it's at 0 degrees. So if you have a glass of ice water that's been sitting around for a while, and it's still got ice in it, can you guess what temperature it is? It's pretty close to 0 because it's got ice and water mixture, and it's been there for a long time. If it's been there for a long time and it doesn't have any ice in it, you can't tell it. You just know it's above 0. But if it's been sitting there for a long time and it's still got ice in it, and it still hasn't all melted, you got a pretty good, and it started with a lot of ice and still has a fair amount, you can pretty much guess that water's at 0 degrees because it's in equilibrium. The ice and the water are kind of holding that 0 degrees, and eventually the air around it will help it melt. But when you have ice and water together in equilibrium, it is at 0 degrees as long as the pressure is at normal. This is all at 1 atmosphere of pressure, by the way. So once you get up to that point where you have added enough energy that you've melted all the ice in your ice water, what happens now? You're adding energy, what's happening to the temperature again?
It's going up.
It's going up again. So we've got liquid that's heating up until we get to what temperature? 100 degrees. Right? It's at 100 degrees.
Sorry, I was looking at the bottom.
That's all right. So it's at 100 degrees now, and we've added almost 200 calories per gram of energy. Then we are adding energy still, and it's staying at what temperature?
100.
It's staying at 100. So what's happening during this time?
Well,
It's boiling. You've got water and steam combined. So you keep adding energy, and it doesn't change temperature. It just changes phase. Right? Changes phase. Look how much longer this line is. How much energy do you have to add to make steam, to make liquid water into steam compared to making ice into liquid water?
that would be just because of the fact that from ice to from your solid to your liquid, it's not actually changing kinetic energy. From the liquid to the gas.
So that's correct. You're not changing the kinetic energy much. Here you're just breaking some bonds. And it doesn't turn out to take a whole lot of energy to break those bonds. But to get enough kinetic energy for it to fly out of the liquid and to break that vapor pressure takes a lot of energy. How much more dangerous is boiling water at 100 degrees when it first starts boiling to boiling water at 100 degrees when it's just ending boiling and it's all steam? How much more dangerous is steam than this water that's just starting to boil?
About 600 calories per gram.
Yeah, it's so much more dangerous. When it becomes steam, and it's coming out of coming out of that spout right before it becomes visible again, that stuff will burn your skin right off. That stuff will burn through most materials. It's got that much energy in it. It'll burn through wood. It'll burn through a lot of metals. It'll burn all kinds of things. Burn through concrete. Okay, this stuff is super energetic, very dangerous. And if you raise its pressure and do this, if you raise the pressure and then go through the cycle and turn it into steam, it'll cut through solid steel, cobalt steel. Okay, that's what they call pressure cutters. You know, these steam cutters. That's what they are. Yes, sir.
So like, those like water jet cutters, is that what that is?
That's exactly what water jet cutters are. They're high pressure steam cutters. So what's coming out is high pressure steam. And then when it hits things and it starts to lose its energy, starts losing energy by cutting things and by being in the air, it turns into water vapor, which is, you know, makes all kinds of messy clouds all over the place. And then eventually it cools off enough to fall to the ground and make a wet mess everywhere. But, you know, yes. You can also do it with cold, high-pressure water, but it's not nearly as powerful. It's also not nearly as dangerous. So. These are also called water lances. You've probably heard that term before, maybe, or steam lances. But that's a lot of energy that we've pumped into the system there, and that's again one of the reasons that we cook with boiling water, we cook with steam. We steam a lot of things. You can cook something extremely quick in a steamer, very, very quickly. So let's look at how we would use this. Oh, we got to go back. Sorry. So how do you determine how much energy you have to put in to melt ice or to vaporize liquid? And it also works in the reverse. How much energy would you have to take out of steam to make it liquid again? And how much energy would you have to take out of liquid to make it ice again? And that's how long are these lines? How do we determine how long those lines are? Well, we measure them. We do the experiment, we measure them, and then we create an equation and we make a constant for every material, just like we did before. And these are the equations for what we call, these are the phase change equations or the latent heat equations. So you have the latent heat of fusion, which is the melting or freezing, depending on which way you're going up or down the graph. And it's Q equals M times F, mass times the latent heat of fusion. Well, then we have the latent heat of vaporization condensation equation, which is Q equals M times L sub V. So it's the same equation, just a different L. And each material has its own latent heat of fusion and its own latent heat of vaporization. And here's the chart. The latent heat of fusion for helium, hydrogen, nitrogen, all these gases, you know, all these solids and liquids, water here. You can see it takes much less energy to evaporate helium, or not to evaporate, this is for fusion, so a lot less energy to melt liquid solid helium, which is hardly a thing, and then it does to melt solid ice. It takes 334 kilojoules per kilogram to melt solid ice. And then it also tells you the latent heat of vaporization. It gives you these in kilocalories per kilogram and kilojoules per kilogram. Then the latent heat of vaporization, how much energy does it take to vaporize water? 2,256 kilojoules per kilogram. Lots of energy to vaporize it, right? And there aren't many that are a lot more than that. I mean, there's silver that's about the same. There's aluminum, which is a lot more. There's copper, which is a lot more and twice as much. Tungsten, which is a little bit more. But really, I mean, even metals, some metals take about the same amount of energy to vaporize as water, which tells you something, right? Water is really kind of a special thing, no doubt about it. And then there are things that take very little energy to vaporize, like alcohol. But that's actually part of the appeal of alcohol to people, is that it vaporizes very quickly and it gets up into the nasal cavities, and it also vaporizes in the blood in the body very quickly, very easily, and makes you drunk. Which I'm not sure really what the appeal of that is, but some people like it, I guess. So anyway, So those are called the latent heat coefficients for fusion and for vaporization. You use them in those equations to calculate the amount of heat that you have to put into something to melt it or to freeze it or to vaporize it, to boil it, or to condense it. To either put it in or take it out. Yes?
For some of them, like, especially at the top of that chart, like helium, nitrogen, oxygen, where it's the latent heat of vaporization is so low.
Yep.
Is that why they typically exist in the gas?
That's why they're a gas, because they always have the amount of energy in normal conditions. Yeah, exactly. All the stuff that exists as a gas in nature have very, very low values for their latent heats of vaporization, and they have low temperatures for those as well. So at this point, I'd like to give one of my favorite questions about physics. It's actually an agriculture question. So this is how the question goes. Well, this is the situation. You guys tell me why this works. And this chart will help you to figure it out. My grandfather was a peach farmer in southern Utah. In southern Utah, it's nice and hot for a long time during the summer, and they have usually pretty warm winters, but it's high enough in elevation in the mountains that they might get a good freeze every year, early in the spring, after the blossoms are on the tree. When you get peach blossoms on the tree, each blossom represents a fruit, represents a peach that will grow there. So if you get a frost and those blossoms fall off, that peach will not grow. It's died, essentially. If the blossom falls off, it's dead. Even if you go out there and just blow them off with a leaf blower, they die. So you do not want to get a frost in your peach orchard in early spring. So if there is a possibility for a frost, my grandpa and other peach farmers would flood their orchards with water from the ditch. They would open up their sluices and the ditches, and they would flood their orchard with a foot of water, 6 inches of water. Okay? And their peach orchard would survive. But they would have ice in their orchard at that point. It would be a little skim of ice on top of this little lake they've created in their orchard. Why did the blossoms not freeze?
Because water could absorb more heat from the blossom.
What is happening heat-wise when something freezes? Where is the heat going to? Where is it going from?
Well, the reason why they survived is it's the same way fish and everything in the water survive, because it's warmer underneath the ice than it is.
Okay, so the ice is colder and the water underneath is warmer, but what about the peaches above? Because the peach blossoms are above the ice, right?
When the water is freezing, the heat is leaving the water and radiating upward.
Ah.
The peach blossoms alive.
So as the water freezes, where does the heat that was in that water go?
Up.
It goes up into the orchard. So every little molecule of ice that freezes releases heat, and that heat escapes upward into the orchard. And so until that freezes all the way solid through, and it never really does, it usually will freeze the top couple inches, and then it will melt during the next day or two, and then it'll freeze again. But as long as that is partially water underneath there and is freezing, it will release heat into the orchard, because that heat has to leave the water for the water to become ice. What's happening is right here. Here's your water that you poured into the orchard. Maybe you pour it in at 5 degrees Celsius, so it's right here. As the water in the orchard gets colder and goes down in temperature, right, it loses this much heat.
Instead of putting the energy in to turn the water from ice to liquid to gas,
We're removing the heat.
Yeah, the heat's
That's right. And then the entire time that ice is freezing, all this heat here, this from this 120 or so calories per gram all the way down to about 30 calories per gram, all that heat is released into the orchard and warms up the trees. It's by no means a fallible method, because you have to have liquid water in the orchard, because as soon as it all becomes solid, then it gets cold, right? It gets really cold at that point. But as long as you still have water, if you put enough water in the orchard, it will work.
So I doubt it ever would in Utah, but if it ever got like completely solid ice, we could just put more water in there?
Yeah, you can put more water in up to a point. I mean, you don't want to freeze the trees out too much.
Yeah.
But I mean, if that at that point your season's dead anyway, because it's just been way too cold of a spring to get good peaches. But I mean, southern Utah is kind of like the South, except at high elevation, so it has that possibility of getting a couple of cold nights and days in the spring. So there's your. I always wondered why they did that, and then when I was studying physics, I learned why they did that. So anyway, so here we have. Let's do it. We're going to do a problem here, which is a classic physics problem. You put some ice cubes in a cup of soda water, and the soda water is at 20 degrees Celsius already. The mass of the soda is 0.25 kilograms, and the ice is at 0, and each ice cube has a mass of 6 grams. So now you know the temperature of the ice, the temperature of the liquid. You have the mass of the ice and the mass of the liquid. And I am going to say that we need to make a drawing. So let's go make a drawing. A drawing. And I highly recommend this when you're doing heat problems like this. So we have our cup. The cup is going to be negligible. It's not going to allow heat to escape or enter in from anywhere. It's a styrofoam cup. And so then we have the liquid inside. And I like to use multiple colors when I do this because we're going to have multiple things. There's my liquid. Mass of liquid is whatever it is. Temperature of liquid initially is whatever it is. Then we're going to have ice in the water. And we have 3 cubes of ice. Right? Each one of them has another mass, which is why I have a different color. And so there's 3 of those at that mass, and there's also an initial temperature for those guys. What's going to happen here?
The heat's going to leave the soda and enter the ice, which is going to provide enough energy.
Heat is going to leave. Here's our soda. Here's our ice. Here's our heat. Heat is going to leave the soda. What letter do we use to represent heat?
Q.
Q. Q is going to leave the soda and enter the ice, right? Now let's go back to our problem really quick. Let's make sure we know what we're talking about. Assume the soda is kept in a foam container so the heat loss unit. Assume the soda has the same heat capacity as water. Final temperature. Find the final temperature when all the ice has melted. So the ice is also going to melt. That's another thing, isn't it? Mm-hmm. So first of all, heat is going to enter. We're going to have heat entering the ice, and it's going to do 2 things to the ice. What's the first thing it's going to do to the ice? What's that? It might change its temperature, because if the ice is at below 0, let's say the ice was put in at negative 50 degrees. First it'll change temperature up to what?
0.
Up to 0. So let's pretend it's going to do that, even if it's not. So first we're going to change temperature. So the ice is going to go from ice at temperature initial to ice, and it's still going to be solid at temperature what? 0. Temperature equals 0. So this is the first thing, and the equation for this process looks like what? It looks like Q equals M times C times delta T, where you use the C of ice, right? And the delta T is going to be this T final minus this T initial, okay? And this is how I recommend you do these problems, because you're going to have several equations you're going to have to put together. You're going to have to solve separately and then add together. So that's going to give you 1 Q going from the liquid to the ice. Then what's the next thing that's going to happen to the ice? It's going to melt. So it's going to go from ice to now, it's going to go to a puddle. And what's the temperature change going to be here when it goes from ice to when it just gets to a puddle? It's going to have a zero temperature change, right? Because it does that all at zero. We found that, we saw that on the graph. When it's melting and when it's boiling or when it's freezing or when it's condensing, it does that, those phase changes at a constant temperature. And for water, the melting, freezing part is done at 0 degrees Celsius. So there's no temperature change here, and there's a different Q. What Q do we use when we're melting, freezing, vaporizing, condensing? Q equals M times what instead of C delta T? Latent heat, right? And this one happens to be the latent heat of fusion for water. So this is going to be mass of ice times specific heat of ice times delta T. This one's going to be mass of ice times latent heat of fusion for ice. And you're good. Now that water is at temperature equals 0. Then what's the next thing going to happen here?
It's going to continue to heat up.
It's going to go from water to water at some temperature final, which we don't know, right? That's what we're trying to figure out. And what's the equation for changing temperature again? It's this one, but we're going to use a different C this time. It's going to be Q equals the M of the ice times the C of not ice anymore. What is it now? Liquid, right? Liquid water times the delta T, and this is the delta T of the ice. This is going to be the delta T of the liquid. Now, in the particular example we're doing, they're telling us that it starts at 0 and goes to here. So you'd only have to use these two equations. But if it started at below 0, you'd have to use all three of them, right? So it starts right here and just does these two processes. Now, what's the water going to do? It starts out as a liquid.
It's going to remain as a liquid.
What's that?
It's going to remain as a liquid. So
It's going to remain as a liquid, right? And what's going to happen in that process?
it's going to lose heat.
It's going to have a change in heat that is going to be equal to the mass of what now?
The mass of the water.
The mass of the water times the C of water times the delta T of the water, right? Which happens to be the same, it's going to have the same T final as the ice, right? So it's going to have T final here. These two are equal. So T final is equal to that T final. And this T initial is equal to whatever it is, right? This one is, I think, 20 degrees or whatever. This is given. Right? Then, what do? You do the same thing we've always done. You use the equations that you have to solve for the things that you don't have, right? And in this case, you have something else that's interesting. The Q that leaves the water is equal to the Q that enters the ice. So the Q blue, dark blue, is equal to the Q light blue total. So the sum of all the light blue Qs. So if you add all these Qs together, they're equal to the heat that entered the water, or that left the water.
And here in like the strategy, it shows one of them as negative since the
Yes, you
water
can.
is losing heat.
So you can say since the water is losing heat, you can call that one a negative, and call the blue one the blue one's positive, and then add them all together to equal 0. I prefer to think of them as going in, going out kind of thing. Either way. But this is the kind of thing that I would recommend you map out before you do this kind of a problem, because then now all you have to do is calculate, plug in, solve, done. With these equations and this relationship, you'll be able to solve for T final.
It does not look fun here, but
It's not that hard. It's pretty easy, actually. It's much easier than vectors and everything else we've been doing.
true.
Difficulty is relative, especially in physics. There are hardly there might be 5 faculty members at this college that could pass this class. Might be. Okay? Maybe. And not all of them are the math teachers on this floor. I can guarantee you that. Okay? This is a very difficult class. And even some of the science teachers couldn't pass this class on this floor, even though they took it at one point. They probably couldn't pass it right now. But difficulty is relative, right? Once you've been through this class and you've just gotten out of the hard part of it, the rest of this is just cake. No problem. So, here we go. Here they talking about ice on trees. Right? So here they're spraying water on the trees to prevent their orange blossoms from freezing. You can do that too. All right. So that gets us into section 14. Let's see. Oh yeah, let's do this next one. How does heat transfer? So here is the here's the question of the day. Another question of the day. You have a campfire, and you can feel heat 3 different ways from a campfire. I'll give you a clue. One of the ways you feel heat is from above the campfire. One of them is from the side of the campfire, and one of them is from what? What is not? It's not below. Below would be the same as from the side. But what's the other way you can feel heat? Usually accidentally from a campfire.
Inside.
Inside the campfire. Okay.
I know that kind of.
Yes, some people have felt that one. Now, let's figure out what methods, how the heat is being transferred in those 3 methods. Touching the fire is the easiest one. Why do you get hot when you touch fire?
Because the heat of the fire goes into you.
Because it's directly in contact with you, right? So anytime 2 objects are in direct contact with each other, they're what we call thermal contact. So heat is going to transfer, okay? That's called conduction, okay? So conduction is direct contact. Which one, how does heat transfer from the side or from the top? The top is probably the next easiest one. How does heat get to you when you put your hands over it? On top of it?
I'm looking at the book. Can I
Hot
still
air
answer?
rises into your hand.
Yeah, the heat from the fire is heating up the gases in the atmosphere around it. And those gases, as they get hotter, move faster. Their density goes down. What happens when you have something of lower density and something of higher density? It floats. So according to whose law? According to whose principle? Not Bernoulli. The guy that ran naked through the streets. Archimedes' principle, right? Archimedes' principle is the thing that says things of lower density rise because of the buoyant force in things of higher density. So that hotter air that is less dense rises into your hands and heats your hands by what we call convection. Okay? So that's convective heating. How do you get warm by fire from the side? Not quite. That would still be convection, actually, or conduction. That describes conduction and convection. But convection is always by rising air currents, and conduction is by touching. And in this case, we're not doing either. So how do you get warm from the side of a fire? It's actually the same way you get warm from the sun. How does the heat from the sun travel through space?
Electromagnetic waves.
Light, electromagnetic waves. Light can carry energy that can be turned into heat when it hits an object. When it hits an object, it excites the molecules and atoms in the object, causes them to vibrate, and heats them up. Specific frequencies of light do that. All frequencies of light do it a little bit, but infrared light does that the most. So infrared light, which the sun gives off and which fires give off in abundance, will heat you up sideways. They heat in every direction, actually, which is why you would get heated that way underneath the fire and above the fire. Above the fire, you also get this is called radiative heat, because it's called radiative because it's radial direction, which means in every direction from the middle point. So it's the radius outward. So that's radiative heating. Okay? So conductive heating, what's the whole idea there?
Touching.
Touching, right? Convective heating, what's the key? It's moving, right? It's movement of air or fluids. That's convective heating, right? Because you can have convective heating in water as well. You have convective heating You can have convective heating in pools, for example. If you heat the bottom of a pool, a lot of swimming pools are actually black on the bottom for a reason. It uses radiated, the black of the bottom of the pool captures the radiative heat from the sun, and then that hot water does what as it gets hotter? Rises to the top, cool water goes to the bottom, heats again, right? So that's another way to heat. That's another convective heating. So liquid can do convective heating. It's not as efficiently, but it also can do it. Then what's the third one? Radiative heating is radiation. It's light coming out from the source. Everything that gets hot emits light because all atoms that vibrate emit light. So anything that has any kind of warmth to it at all, anything that's above 0 Kelvin is vibrating and creating light of some wavelength.
It just might not be measurable to the naked eye.
Well, yeah, the naked eye can't hardly see it at all because it's mostly infrared. But it can go higher. Things, become white hot, for example, or blue hot, or yellow hot, or red hot. We have those phrases that we use, but those literally mean what they mean. So, something that is white hot, for example, is emitting every different color in the spectrum that we can see, and then it's also emitting some ultraviolet, which we can't see literally, technically, but we can detect it with our eyes. Ultraviolet at high intensities looks white to us. It looks kind of beyond white because it's burning our retinas. Yeah, so you get a little bit of ultraviolet from the fluorescent tubes for sure.
Look at that long enough and it burns your retina.
No, it's not bright enough to do that. And they block it. They block some of it as well. So anyway, so well, next time we'll talk about how we can how we can calculate and measure conduction, convection, and radiation. So that's start off the day tomorrow. All right, we're done.
Yeah, I have some questions about the calculus physics.
Okay.
I was able to make it.
Just give me a minute here.
Okay.
Okay, I'll see you later.
Okay, see you, Cassidy.